Hello everyone and welcome to Lecture. So today what I want to be introducing and starting to talk about is some of the material from Chapter 11 in the book. And specifically this is going to be parametric curves, polar coordinates, and the polar form of curves. So this material will be from 11.1 and 11.3 of the book that we're using. And I'll start by defining what a parametric curve is and giving you a number of different really good examples of a parametric curve so you can kind of get an idea of exactly what we're talking about. So suppose that we have two functions f and g, and that x is the function f of some parameter t, and y is equal to the function g of this same parameter t for two different functions f and g, which depend on t, and t is in some interval of real numbers from a to b. And we say that this t is called the parameter of the curve. And you can, in some sense, think of this as a number of different things. A very common parameter is time, but you can also use really any other geometric quantity as the parameter. So we'll see polar curves use the parameter of angle to describe points in the curve. But the parametric curve itself is the set of all points in 2D, x comma y, such that the value of the point, the coordinates of the point, are exactly the value of the function f of t. So the x coordinate of the point is f of t, and the y coordinate of the point is g of t. And if we think of t as being in the interval from a to b, this forms a curve in 2D. So for the first example, I'm going to write down x is equal to 2 cosine of t. So 2 cosine of t is our function f, and y is equal to 2 sine of t. We're going to consider this for t, the parameter in the interval from 0 to pi over 2. And well, we want to get an idea of what this looks like. In order to do that, we can try and fill out a table with the value of the point. So the value of the parameter in one column of the table, and the value of the point in the other column of the table. And we see that we have the first value, 0. The point is going to be 2 times cosine of 0, which is 2 times 1, or 2. And then the y coordinate of the point is going to be 2 times sine of 0, or 0. We'll do the midpoint of this region as well. So when t is pi over 4, the x coordinate is going to be 2 times cosine of pi over 4, which is 2 times 1 over the square root of 2, or 2 over the square root of 2. And the y coordinate will also be 2 over the square root of 2, because the y coordinate will be 2 times sine of pi over 4, which is 2 times 1 over the square root of 2. And I'll just do the endpoint as well. This is going to be 2 times cosine of pi over 2, which is going to be 0. 2 times 0, which is 0. And 2 times sine of pi over 2, which is going to be 2 times 1, or 2. So these 3 points are on this curve. This right here is a visualization of these 3 points on this curve. I'm talking about the interval from 0 to pi over 2 here, and the x coordinate f of t is going to be 2 cosine of t, and the y coordinate is 2 sine of t. And filling out this table for more points is definitely cumbersome, so I don't recommend doing this by hand. It's best to use some sort of tool like a graphing calculator or GeoGebra to kind of plot this out. So for 3 points, we have these 3 points that we've shown are on this curve. If I increase to 4 points, these 4 points are now going to be on the curve. And if I continue to do this process with more and more points, I will continue it all the way up to 100 points, which would be very, very cumbersome to do by hand. We can see very clearly that these parametric equations are giving us the equation of a circle of radius 2. This circle right here. So this is very, very neat, and this is the idea of a parametric curve. Now, specifically, the interval of t really defines for us which points are going to be on this curve. And as we saw in the plot, and also as we're kind of seeing here, this 0 is the beginning point of the curve, and t equals pi over 2 is the end point of this specific parametric curve. So really what we're getting for this parametric curve right here is a quarter circle, or a quarter of a circle, in quadrant 1. So it's a quarter of a circle in quadrant 1. If we wanted to get the full circle, we would have to look at the entire range from 0 to 2 pi for our angle. And this will be important later on in the lecture when we introduce polar coordinates. We can directly verify this by looking at x squared plus y squared and showing that, in fact, x squared plus y squared does satisfy the equations of a circle. This is going to be 2 cosine of t squared plus 2 sine of t squared, which is the same thing as 4 cosine squared plus 4 sine squared, or 4 times cosine squared plus sine squared, which is 1. So we've shown that for this parametric curve, x squared plus y squared is in fact equal to 4, which is the equation of a circle of radius 2. For the next example that I want to consider, I want to show you what is called a cycloid. So the parametric equations of a cycloid are given by the following functions of x and y, parametric functions. X is going to be equal to r times t minus sine of t, and y is going to be equal to r times 1 minus cosine of t. And we'll just consider this for the parameter value from 0 to equal 0 to 4 pi. You can definitely consider it for different ranges, but we're just going to look at this for the range for the parameter from 0 to 4 pi. Now, like I said before, you can go through and plug in various points and make a table of points, but this is kind of cumbersome, so we don't want to do this by hand. But this GeoGebra applet that I wrote is very, very helpful for doing this for general parametric curves. This is the first 2 points, the endpoints on the curve A and B here. This is the first point when t is 0, and the last point when t is 4 pi. If we increase the number of points to 3, we see that these 3 points are on this curve. If I increase to 4, these 4 points will be on the curve, and so on and so forth. And so this is what we're seeing as we increase the number of points that we're sampling on this curve. And just like before, if I increase to 100, we can see a very nice picture of what this curve is looking like. And sure enough, if we plot the continuous parametric curve and remove these points, right, this is exactly what a cycloid looks like. And now you may be wondering where these parametric equations are coming from. And while I'm not going to go over it right here because it's a little bit of a long derivation, it's really just using some algebra and looking at the equations of a circle that starts at this point right here, so x equals 0 and a distance of r away in the y-axis. So starting with this circle and tracking this point right here on the circle as the circle is rolled along the x-axis at a constant rate r with respect to the parameter t. So you can think of t like time and the rate or the radius of this circle being r, and as we roll this along the x-axis and consider tracking the point of the circle and what it does, the cycloid is exactly the curve that gets traced out. I think this is a very nice demonstration of what this curve is coming from. If you change the value of r, the radius of the circle that's being traced out, the cycloid gets smaller or larger. But this is a very neat example of a parametric curve, and it is also a very important example in physics and in mathematics. So an extremely useful tool for us going forward is going to be the idea of the polar form of a curve, and specifically the idea of polar coordinates. And basically what polar coordinates are an alternative description of the two-dimensional space, 2D Cartesian space. So here I've just kind of drawn a picture, which is typical two-dimensional space expressed in terms of our Cartesian coordinate system. So for example, take the point P, which is the point x equals 2, y equals 2. This point right here. This is the point x equals 2, y equals 2. We'll call this point P, just for example. The Cartesian coordinates are x equals 2, y equals 2. Now, we also know that this point is a distance of 2 times square root of 2 from the origin. And this is just, you can treat this from Pythagorean's theorem. It's going to be the square root of 2 squared plus 2 squared, which is the square root of 2 times 4, which is 2 times the square root of 2. So this point P lies on a circle of radius 2 root 2 away from the origin. That's the radius of this circle that I've just drawn right here. If we also consider the angle of this point P away from the x-axis, this is something that we can go through and compute directly using trigonometry. So we have that the radius RP was 2 root 2, and we also have an angle out to P, called an angle theta P. The theta P satisfies, from basic trigonometry again, tangent of the angle is the opposite over the adjacent. So tangent of theta P is going to equal 2 over 2, or 1 in theta P, then is going to be equal to the angle pi over 4. So we have two separate values now, Rp and theta P. That is a nice way of expressing the location of this point P. Right? You can express it in terms of what are called Cartesian coordinates, or its x and y coordinates, or its polar coordinates, which is its r coordinate and its theta coordinate. So in terms of polar coordinates, P has the expression, point P has the expression 2 root 2 comma pi over 4, where this is Rp, the radius of that point, theta P. So this example encapsulates the essence of polar coordinates. You can do this for any other point that you want to do it for, and you'll be able to see how to take that point and describe it in terms of polar coordinates. But the point here is that we can do this for any other point that we want to, x comma y. So for any point in two-dimensional space, right, we can do this out. And so I'm going to do this for a number of different other points. And get a picture that looks like this, where you have, say, circle of radius 1, circle of radius 2, circle of radius 3, circle of radius 4, and so on and so forth. Right? And then you also have straight lines now, which denote constant angle from the x-axis. This grid that I've written down right here, you can see now it forms a grid. It's the grid for polar coordinates. So, for instance, right, this point right here, is going to have an x-coordinate of this x value right here. It's going to have a y-coordinate of this y value right here. And it's going to have an r-coordinate of whatever the radius of this circle is, and a theta coordinate of whatever angle this angle is out to the point. And we can do this for any point in two-dimensional space. So for a given point xy, in Cartesian coordinates, we know that the relationship between the radius out to the point and the angle is going to be r times cosine of theta, and the y-coordinate is going to be r times sine of theta. So these are the transformation equations to get from polar coordinates. If you have a given angle theta and a given radius r, these equations will give you the x and y coordinates of the point. This is conversion from polar to Cartesian. And it's mainly just based on the idea of, let's say we're going to this point right here, looking at the triangle formed when going out to that point and relating the angle theta and the radius to the x and the y coordinate of that point. So these equations give us the conversion from polar coordinates, or r comma theta, to Cartesian coordinates x comma y. And furthermore, if we want to go from Cartesian coordinates to polar, or values of x comma y to values of r comma theta, the defining equations are going to be tan of theta is equal to y over x, and x squared plus y squared is equal to r squared. Now, it's really important for me to point out that polar coordinates in general are not unique, because we can allow for many different possible polar representations of a given point. Right? Cosines and sine functions repeat themselves after an angle of 2 pi. Right? So, for instance, the angle of pi over 4, radius of 2 square root 2, the point that we considered earlier, has the same polar representation as the point of the same radius, 2 root 2, in an angle of pi over 4 plus 2 pi. Right? So there are infinitely many polar coordinates associated with any given point. It's also important for me to point out that we can allow for negative values of the radius r. This is due to the fact that the general equation relating x and y here is x squared plus y squared equals r squared. And so because each of the quantities x, y, and r are squared in this expression, right, any one of these could be positive and or negative, because when we square them all, all of the terms are going to be positive. So I think to best explain why this is important and why this matters, we'll see why it matters a little bit later with examples, but let's just describe this. I'll pick a point Q here, take this point Q, where the x coordinate of the point will be right here. So it's this x value, and the y coordinate of the point will be right here, this value right here. But in terms of the polar coordinates of this point, it's very, very nicely described by going out to a radius of 2 and then rotating around all the way until we get to an angle of 5 pi over 4, or pi plus pi over 4. So this point Q has polar coordinates r theta of the distance out to the point, which is 2, comma, the angle 5 pi over 4. We can also describe Q in infinitely many other ways. Specifically, I can describe the coordinates, the polar coordinates of this point Q as -2, comma, pi over 4. Now, why is this? This is maybe something that you haven't seen before, but it's perfectly valid to do this. So why can we do this? Well, the answer is that it all has to do with this arrow right here, which is called the initial ray, associated with how we're describing the point. This initial ray, this remember is coming from this first description in polar coordinates, 2, 5 pi over 2. The initial ray goes out to 2 and then rotates around to the angle of 5 pi over 4. If instead you have a negative value for your radius, this initial ray is going to point in the opposite direction. It's going to point along the negative x-axis. So in this case, the initial ray, for the second description here, will go out to -2. X equals -2. This is the initial ray for this description right here. And I'll underline each of these in the colors corresponding to the initial ray for each of these. So if our initial ray goes from the origin out to x equals -2, this is still a distance of 2. And then we only have to go an angle of pi over 4 from the x-axis, which corresponds to this angle right here. Either description works in describing this point and will give us a good description of the point Q. And it turns out that this is a very, very important thing to consider, because we will have equations that will give us negative r values. We need to be able to kind of consider this. So this is what happens with general polar coordinates. The point descriptions are not unique. It is possible to obtain a unique description of points in polar coordinates if we restrict the range of values for r and theta. So typically, you have a standard restriction that you can use if you're only interested in a unique representation for a given curve, and that's to make sure that the r radius is only positive so this initial ray only points along the positive x-axis, and theta goes from 0 up to, but not including, the angle 2 pi. So if you restrict and you make sure that r and theta stay within these ranges, then you do obtain a unique representation for every point and a unique mapping between points in Cartesian and polar coordinates. But in general, if there's no specification for the restriction, you have to assume that you're dealing with general polar coordinates, which is not necessarily unique, as I evidenced here with this really nice example. And so to give you some intuition for what's going on here, I want to show you an application of polar coordinates to image data. This is an image of a cat, and I'm just going to show you what happens when you transform this image into polar coordinates, and we'll see kind of how the image distorts as you go from Cartesian into polar coordinates. So you can hopefully see that the new image has regions where the area is stretched and kind of altered. And this is going to be important when developing new formulas for areas when integrating in polar coordinates. This is a big concept in Calculus 4, but we will even see it in the next few lectures when we start talking about polar curves and integrating areas and solving for areas using polar coordinates. So the last topic that I want to touch on is the topic of the polar form of a parametric curve, which is a very, very useful topic and way of describing curves. And the main idea here is that any curve for which we have R is a function of theta, the angle theta, in its polar form, can be written parametrically, or as a parametric curve, which depends on the parameter theta. So the main thing here is that we have the radius for a parametric curve is a function of theta, and the points on the parametric curve, x, y, we know in polar coordinates are going to be r cosine theta, r sine theta. And so then if we know r as a function of theta, this is going to give us the x-coordinate is going to be parameterized by theta as that radius function of theta times cosine of theta, that's the x, and how it's parameterized by theta. And the y is going to be r sine theta, which is f of theta times sine theta. For theta in some range from A to B. And I want to give you a number of different examples of how to do this for a given curve and how to kind of think of curves like this. A good example is the exponential spiral, where r is equal to e to the omega times theta for theta in some interval. Just take for theta in the interval from 0 out to 10 pi. The x and y coordinates of this curve then are going to be r cosine theta, so e to the omega theta times cosine theta. The y coordinates of points in the curve are going to be e to the omega theta times sine of theta. And depending on whether omega is positive or negative, we get a spiral growing away from the origin or spiraling inwards towards the origin. You can verify this by plugging in for a number of different values of theta. So I encourage you to do this by hand. I'm going to do this for the first couple of values here graphically, so you can see 2 points on this curve, A and B, the endpoints. When you get 3 points, you get an additional point right here. When you cut up the interval into 4 points, you get these 4 points, and so on and so forth. As you keep adding more and more points to this curve, you do start to slowly see this spiral take shape. But to really get an idea of what this curve is, you want to add a pretty large number of points, which is not feasible to do by hand. But this is 200 points plotted out. And I think you can very clearly see that what you're getting here with this curve is exactly this spiral that's moving inwards as theta increases. This is because I've chosen an omega value of negative 0.1 here. So the radius is decreasing exponentially as your parameter gets larger and larger in the interval of the parametric curve. The next example that I want to go over is what's called the cardioid. And this is the polar equation where you have that r is equal to 1 minus cosine theta. So for points on this curve, they satisfy r equals 1 minus cosine theta for theta in some interval from a to b. Which will give you the equations for x as 1 minus cosine theta times cosine theta, and y 1 minus cosine theta times sine theta, using our relationship between the radius and cosine theta and sine theta from polar coordinates. I'm going to go through and do my sampling procedure for this curve, just like before. It's definitely possible for you to do a number of different points in this curve, but I just want to show what this curve looks like when we kind of sample a number of different values. This is for a from t or from theta from 0 to 2 pi, so all the way around here. The shape that we're getting is sort of like a very similar to a heart, and this is why it's called the cardioid. This is what we get for this curve. So this will be important for our example applications. And the last example of a polar curve that I want to give for right now is called the rose curve. And this is whenever you have a relationship r is equal to, say, cosine of n theta, and this is on some interval from a to b. this is going to generate x equals cosine of n theta times cosine of theta, because this is r times cosine theta, and y will be cosine of n theta times sine of theta. So if we gradually sample a number of different points on this curve, and we kind of look at more and more points in this curve, we eventually see why this curve is called a rose. This curve is a rose because it looks like a flower. And starting at initial value here of negative pi over 6 all the way up to pi minus pi over 6 will give us the following curve. It's traced out like this as we go through and look at the different values for the angle. And one of the important things that we're going to do in the next few lectures is figure out how to deal with both derivatives tangent to parametric curves and also integrals. So try to find the area of regions like this using the definite integral. So for instance, we'll look at say you want to find the area of an individual petal of this curve. You'll want to be able to go through and figure out what the correct bounds for theta is, the angle, and then go through and compute the actual area in, say, one petal of this curve. So like if we kind of visualize just this one petal right here. So I just plotted out the full curve. One petal of the rose curve will now look like this. Now I want to be clear, this is the rose curve for the value of n equal to 3. But we can certainly study it for different values of n. So for instance, I want to say consider what it looks like for the value of n equal to 2. So r of t here is 2 cosine of 2 times t. This is another different visualization of what this is going to look like for different the theta angle for different values of t and the corresponding point on the curve. So an interesting question, like I said, would be the area contained inside this curve. This is what we're going to be investigating in the next few lectures. So we'll look at the derivatives tangent to this curve, and we'll also look at the area that's kind of trapped inside the curve as it traces out through its parameterization. The final thing that I want to mention is that for some curves, the curves look simpler in Cartesian coordinates, and for other curves, the curves look simpler in polar coordinates. So we want to get really good at practicing how to convert a given polar curve to a Cartesian curve and vice versa. And so I'll do a number of different examples of this right now just so you can see. So let's say we have a very simple line, the line x equals 3. You know what this looks like. It's a line on the xy plane corresponding to x equals 3. So x is 1, 2, 3. This is going to be a straight line. And it has a very simple equation, algebraically, x equals 3. In polar coordinates, this is going to be the relationship r cosine theta is equal to 3, which is the same thing as the equation r is equal to 3 over cosine of theta, which admittedly is a little bit more complicated than the original equation in Cartesian coordinates, but is a good example to show how to convert between these two systems of coordinates relatively easily. For a more complicated example, take the hyperbola, which you saw on the previous written assignment. This curve, very quickly here, looks like this. You have an asymptote right here, and you have an asymptote right here. And this is x equals 1, x equals -1, right here and right here. This has the Cartesian equation, x squared minus y squared is equal to 1, which in polar coordinates is going to be r cosine theta squared minus r sine theta squared is equal to 1. Or if we factor out an r squared, we'll get that r squared times cosine squared theta minus sine squared theta is equal to 1, or r squared is equal to 1 over cosine squared theta minus sine squared theta. And the alternate form of cosine squared theta minus sine squared theta from the half angle identity is 1 over cosine of 2 theta. So the hyperbola in Cartesian coordinates has this equation, but in polar coordinates it has this equation. R squared is equal to 1 over cosine 2 theta. So it's arguable which one is simpler. I think the polar coordinate expression is a little bit nicer, but it depends on how you feel. It's a little bit subjective for this one. The last conversion example that I'll go over right now will be that of a circle that's shifted away from the origin. And we'll just put in some numbers to make it a little bit more tractable. So this is going to be the circle that shifted by 3 away from the x, or the origin in the x direction. So x minus 3 squared plus y squared is equal to 9. So this is one way of writing down the equation of this circle, which is going to look like the following. This is x equals 1, 2, and then 3. The circle is going to have a radius 3 and be shifted by 3 away from the x-axis. So it'll look like this. Yeah, a little bit bigger. Right there. And so this is what the equation of a shifted circle looks like in Cartesian coordinates. We can expand this term right here to get x squared minus 6x plus 9 plus y squared is equal to 9. And these two 9's cancel one another. So this is the same thing as the equation x squared minus 6x plus y squared is equal to 0. This is the Cartesian form of this equation. You can write this one or this one. But if we notice very nicely that x squared plus y squared is the same thing as r squared, then this nice equation in Cartesian coordinates becomes for us in polar coordinates r squared minus 6 times r cosine theta is equal to 0. Or, rewriting, dividing out by r as long as r is non-zero, this will be r minus 6 times cosine theta is equal to 0, or r is equal to 6 times cosine theta. So this is the equation of a shifted circle of radius 3 shifted away from the origin by 3 in x in Cartesian coordinates. And this is the equation in polar coordinates, which is much, much simpler than the original equation. And this is something that polar coordinates will tend to do for us, is simplify things that are related to circles. But I think this is all for today's lecture. Thank you very much for tuning in. I hope you had a fantastic day and that you learned something.